In this video, we're going to talk about the limit comparison test. Now, the limit comparison test is one that I think is really useful. Some people think that it's kind of a difficult test to use because every time you use it, it really requires finding what's called an end behavior model. I'm just going to write end behavior model over here. And what that really entails is looking at the highest powers and looking at what kind of makes the function behave the way it does, what makes it look the way it does. And we call that end behavior model B of n in this particular definition of the test. Okay. So you'll notice, first of all, that we should be talking about positive terms. And what we're going to do is we're going to create an end behavior model, and we're going to take our original series, divide it by the end behavior series, and find the limit. And essentially, if we can get the limit to be positive, we can get it to be greater than 0, then there's agreement. Meaning, if our end behavior model converges, then our series converges. If our end behavior model diverges, our series diverges. So we really can get what I always call agreement. Okay, if our end behavior model converges, the series will converge. If our end behavior model diverges, the series diverges. Here's how I always pick my end behavior model. Let's look at this first one. I look and I say, well, the highest thing on the top is 5n. Highest thing on the bottom is n squared, and I simplify. So my b of n is 5n over n squared, which I would simplify to 5 over n. So the test says take your original series, so this whole big thing, okay, so let me write the whole thing, 5n minus 7 over n squared plus 6n plus 1, divide it by your end behavior series, okay, so we said 5 over n, and evaluate the limit as n approaches infinity. Well, instead of dividing by a fraction, I'm going to multiply by the reciprocal, so n over 5. So what that gives me is a limit as n approaches infinity of 5n squared minus 7n over 5n squared plus 30n plus 5. And now what you can see is we have the same power on top and bottom. We use the coefficients. The limit is 1. And the limit's greater than 0, so we have agreement. Now, I'm just going to write greater than 0. So this may be what I should have done at the beginning, and I kind of got going and I skipped it, is if we look at this original end behavior model, if we think about that, we say that series, 5 over n, this is a divergent P series. Okay, divergent because remember, anytime the power, if it's something over n and the n isn't to a power greater than 1, it diverges. It would have to be, n squared, n cubed, n to the 1.1. But this is a divergent P series. So our end behavior model diverges, and we got a limit greater than 0 when we did the quotient, so that must mean our original series also diverges by limit comparison test. Okay, let's look at this second one. And again, I kind of just go to the highest power on top and bottom, go to the stuff that dictates the shape, and I create a n cubed over 7n to the 6th, which is the same as 1 over 7n cubed. And maybe let's just right away look at that end behavior model series. 1 over 7n cubed as a series, that is a convergent P series because the power is greater than 1. Okay, right here we have n cubed in the denominator, so that's a convergent P series. Maybe I'll just kind of put a little box around this so we have it. Okay. So now when I set this up, I take my original and I divide it by the end behavior series, which I'm just going to, right away, I'm going to multiply by the reciprocal. Limit as n approaches infinity. And if you look at this, if you multiplied it out, you'd have 7n to the 6th when you multiply those two together, and you've got this 7n to the 6th on the bottom. So the limit is going to be 1, which is greater than 0. Remember, as long as we get a limit greater than 0, we have agreement between our end behavior model and our original series. Well, our end behavior model series converged, so this series must also converge by the limit comparison test. Let's do a couple more. Now this first example I'm going to show you is a little bit different in that as you look at the terms, those high powers to set up your end behavior series, it comes out negative. And remember, we said that these sequences, these end behavior models and things should be positive, but I wanted to show you that actually, for something like this, a simple polynomial on top and a simple polynomial on the bottom, even if it's negative, it will still work. Okay, so this is a divergent P series, and excuse me, yes, it is. You really, a lot of times you are comparing to P series, so I would know that rule down pat. Remember, it's n to the first. To converge, n would need to be, the power would need to be greater than 1. So if I take my original and divide by the end behavior series, same as multiplying by the reciprocal, and I take the limit as n approaches infinity, what you'll see, if you can think about this a little ahead of time, multiplying these two together, you get negative 6n to the 5th, negative 6n to the 5th, same power on top and bottom, use the coefficients, you get 1. So we have agreement. So this original series must also diverge. Remember, you set up that series. It's so important to set up a good end behavior series, because once you've done that, it's pretty easy, and the limit usually does come out to be 1 if you set it up correctly. Let's look at the next one. Now this one I think you could probably make a good guess about just based on a geometric series, but let's take a look at how you could do it with limit comparison, because direct comparison wouldn't work. You're making the denominator here smaller by subtracting 1, so you can't compare to the geometric series 1 over 2 to the n. I'm just going to make a note. There's no direct comparison you can do to 1 over 2 to the n, because, as I said, you're making the denominator smaller. Therefore, you're making the series or each term larger. So we're going to do it by limit comparison. The highest thing on the top, well, there's only 1, and the bottom is 2 to the n. So I'm going to set it up as 1 over 2 to the n. This is a convergent geometric series. Okay? Remember, anytime, because it's the same as 1/2 to the n power, and anytime the ratio is less than 1, or between between -1 and 1, you are converging. So if I take my original series or sequence and divide it by the end behavior, same as multiplying by reciprocal, you take a look, 2 to the n, the limit will be 1, which is greater than 0. So again, you couldn't do it by direct comparison. Because direct comparison, if this were a plus 1, we could do it by direct comparison. We'd say, well, 1 over 2 to the n converges, and 1 over 2 to the n plus 1 is even smaller, so it must converge. But we didn't have that, so we had to go to limit comparison, which worked really, really slick. Limit comparison is a really nice test for a lot of different a lot of different things, especially for like a polynomial over a polynomial, because all it becomes then is judging how far apart the powers are and setting up a nice P series. But setting up a nice little geometric series works well. All right, last one. 1 plus the natural log n over n squared plus 5. Well, it's a little hard to maybe pick this out, but the most powerful thing on the top is n, because remember, if you have a number and you take the natural log of it, especially as you go out to infinity, natural log makes it makes it smaller. 100 versus the natural log of 100, 100 is larger. So n is the most powerful thing, and n squared is, of course, the most powerful thing on the bottom. So our n behavior series, n over n squared, is just 1 over n. This is a divergent P series. Remember, this is the harmonic series. It diverges. Remember those P series. Really, really know those rules. Okay. So I take my original. I divide it by the new series, same as multiplying by the reciprocal. And what I'm going to get is n plus n squared natural log n over n squared plus 5. Now this is kind of tricky, because you certainly see that the highest power is n squared on the top and on the bottom. But it's not just a number times n squared. It's not just, as simple as saying, that like up here, that we could just use the coefficient. It's not like that. But I want you to think about this. If you really looked at this and you said, well, this is almost going to simplify to just natural log of n, thinking about that that coefficient, that natural log of n would give you the coefficient of n squared. As you go towards infinity, obviously this would grow towards infinity. The natural log of infinity is infinity. And you might say, well, that doesn't help me at all. No, it does help you, because in limit comparison, all you need to do is be greater than 0. And most of the time I've set up these n behavior models to be just, so it all works out that the limit is 1, but it really doesn't matter. As long as you get a number bigger than 0, you've satisfied the limit comparison test. So you look at this and say, well, geez, this is, n plus n squared natural log of n. Obviously, this is bigger than n squared plus 5. It's going to grow towards infinity, right, which is greater than 0, which means we have agreement. The n behavior series diverged, so this series must also diverge.